3D Gaussian Splatting's quality is highly sensitive to the capture set and camera placement. In standard viewers, the scene shows hundreds or even thousands of camera flash through, cluttering the display and making it hard to tell which cameras explain the specific region or the current view. We present CamView, a framework for visualizing 3D reconstructions datasets in scene space, enabling users to understand which cameras and images support each region of the reconstruction. Our pipeline starts from SFM results that include camera poses and sparse points. We construct the camera view graph via co-visibility, perform hierarchical clustering to obtain a multi-level hierarchy, and visualize it in an LOD viewer that highlights few relevant cameras. We will break down the details of each step starting from view graph construction. First, we take the SFM output, which include camera poses and a sparse point cloud, to construct a view graph. We construct a graph G, V, E, X, where V are camera points, E are edges encoding pairwise visual correlation between camera, and X are the node features given by the positional encoding of each camera's 3D positions. For each camera pair ij, we project their observed 3D points and define the edge weight as the size of the overlap. We use this value directly as wij. For node features, we apply a nerve-style positional encoding to every camera center, mapping its 3D coordinate to a higher dimensional representation. For the graph refinement, we remove long-range edges with a distance threshold to suppress spurious links, then compute connected components to partition the graph into disjoint camera tracks. The resulting print graph serves as the input to our hierarchical clustering. Next, we will break down the hierarchical clustering step. From the clean view graph, we build the graph Laplacian that summarizes the connectivity strength between cameras. Using the graph Laplacian, we run a graph convolution, which is basically a low-pass filter on the graph. The result is a similarity matrix that we feed into spectral clustering. Next, we run spectral clustering on the similarity matrix to split the cameras. We recurse on each subcluster and stop when either the tree reaches a maximum depth or a cluster falls below a minimum size. This produces a clean, multi-resolution camera hierarchy for the LOD viewer. Finally, we render the hierarchy in a LOD viewer that adapts to the camera's proximity to each group. When the user camera is far, the view is coarse. The champion camera, which is the closest to the currently viewed image, is highlighted as red, and each cluster shows its representative camera in blue. As we move closer, distant groups collapse while nearby groups expand, revealing more cameras. As we can see on the right, the refined view exposes deeper levels of the hierarchy and a denser set of cameras around the current viewpoint. This is a short demo of how the visualization works. We show the hierarchical tree on the top right of the user view to demonstrate how the LOD works based on our constructed trees. We observe the image that is shown in the viewer is updated dynamically based on the distance of the user camera to the scene and point cloud representation. These are our qualitative results on sample dataset from MIP-NERV 360 and our own 3D reconstructed model. Our tools provides level of detail visualization for SFM camera scenes, enabling clear comparison and deep understanding of the data used for reconstruction. For the next step, more analysis and visualization on the quality of the views will be done. Thank you.